All right, welcome back, everyone. Let's see. Hope you all had a good break. I think we have some new people in here. So I'm just going to go give a quick rundown over what we've been trying to do in this session, and just so everyone can get up to speed. So this is the breakout session for lunar research and extraction, processing, and handling of in situ resources. And so we wanted this to be a very broad session. So the questions that I was looking at are pretty broad there. That I just start for some discussion questions here, which if I can find the right window, I will pop up. There we go. So we're looking at technology gaps for the various resource extraction and handling things. That can be everything from water and oxygen to metals to lunar cold volatiles. We're discussing about how we can go about advancing the TRL for these various technologies. So, demonstrations, fundamental science. We had a lot of discussion about the drawbacks of various techniques and what we need to know to be able to look at actually implementing some of those techniques on the lunar surface through autonomous systems. And then we were also discussing some of the most promising or the most immediate need for various technologies in the short, mid, and long term. And then also another question, which I don't have on here because it's one that came up. There was quite a bit of discussion about where we need to actually to work on these technologies, whether that be whether it's something that we can do here on Earth via microgravity simulation, like parabolic flights or drop towers, whether we can do it on ISS and low Earth orbit, or whether their technologies actually have to be developed on the moon. So with that being said, I know we have a bunch of new people in here. So any of the new folks have any particular opinions on any of those questions, or this is not meant to be just limited to these various questions. These are just some to get started. But also feel free to bring up any related discussion to this technology, no matter how far out there. I'd like it to be very freewheeling. I know the earlier session, we ended up into a long digression into ionic liquid technologies for recovering things. So really, anything that's relevant. So with that being said,
I have a comment. I noticed that most companies which are working on in situ extraction of something are targeting at just one component. It can be oxygen, water, sometimes volatiles. However, very few people are thinking about complex processing of the regolith, targeting no waste. Regolith is composed by chemical elements, and most of them are useful. With careful planning, all of them are useful. And in principle, it is possible to extract volatiles, extract metals, extract cement, make concrete, make bricks out of regolith, and have very little or none of the leftovers. Complex processing of regolith is a problem, and right now there is no sufficient funding for designing it.
If you don't mind me jumping in, this is Gio from Teraxis. Am I able to share screen just to show one chart from what I presented earlier?
Absolutely, you should be able to.
Awesome. I'm not used to Teams. Where's the magic button? There it is.
Yep, little white box, the black arrow.
Yeah, okay. So one moment. So Nikolai, I don't know if you were in the earlier presentation, but we've been working on a vacuum pyrolysis reactor, which is a ultra high temperature, essentially vacuum reduction furnace. And this chart here is showing at a pressure of 100 pascals, which is around the pressure regime we operate, how the common components of ordinary regolith get reduced into other.
Just to jump in here, I think you're actually showing your internet browser right now than a chart.
Oh, whoops! I am showing you Wikipedia.
Well, I mean, if Wikipedia says it, it must be true, right?
I will show you. Is this now the right screen?
That looks like a chart, yes.
Awesome. So I guess we'll stop looking at silicon monoxide Wikipedia page, and we'll look at this chart instead. So this is from actually a paper from 2006, and I'd have to go find the paper again for the specific details, but our reactor is designed to operate at and above 2000 degrees C, where we can then begin to capture out silicon monoxide or elemental oxygen or elemental aluminum, iron, titanium, etc. Our primary focus was the oxygen side of things because that's kind of the low-hanging fruit for what people really need on the moon. But as a byproduct of this process, because oxygen, we essentially condense out at the very end. Before we get the oxygen, we have to condense out all these other elements. So if anyone has a use for, let's say, silicon monoxide, we can probably produce quite a bit of it because that's what's going to fall out of this process when we get past this critical temperature.
How do you separate the gases?
Well, that is a great question.
So we have a condenser with a thermal gradient, and we just keep the thermal gradient appropriate, and then we can condense out the elements. It's a bit of a question how pure those elements are going to be.
Right.
It's probably going to be more on the 70% target element, 30% other stuff.
And our focus to date has been on the power side of things, actually being able to reach and sustain the temperatures we need in our reactor. But the separation and purification, I guess, process is one of those big things that needs to be sorted out. But fundamentally, right now, we're doing a temperature-based filtering.
Yeah, and it's not only the temperature, it's also the high temperature, and then you have to supply quite a bit of energy to drive those reactions.
Condensed iron or aluminum will be solid or liquid? Will they be melted metals?
They come out as gas, and then we condense them to a liquid. And then we would solidify it.
Great. So you condense liquid metals, and then you can pour a liquid metal into a form and form some parts, metallic parts.
Or we can then do extruder and 3D print with it.
Right. Yeah. Provide a base powder for a specific printer, perhaps.
So
how does your reactor handle corrosive gases?
So we looked at atomic oxygen, and we basically used already oxidized materials as a condenser to prevent oxidization. We haven't looked at any of the other minority constituents, sulfur, and how they would react.
Right. We haven't touched that yet.
No.
Okay. Yeah, because I mean, not to harp back on the same thing, but it's easy to distill these things when they're in a different form, like say in their halogen forms, especially the chloride forms, right? That's what they typically do. So that's the easy way of separating them.
Yeah. So if we were going to, I mean, there's layers and layers of complexity, right? Up to setting up your own foundry to make specific alloys, but from a first cut, if we were focusing on oxygen extraction, I think it would be, we have oxygen, we have a process that captures everything that's not oxygen, and then we have a process that captures the oxygen, and the not oxygen is a combination of all these different things, perhaps all even in the same kind of like volume, and we could treat it as waste if we didn't really care about it, or we can try to think of ways of turning it into a form that's usable for a customer. So, if there's specific processes out there that are like, oh man, I really want molten iron, and like molten iron is going to solve so many problems, then we would design a specific part of the process that can enable that.
And we've been thinking about this as a two-phase kind of deal where we first start with oxygen, learn all the lessons, have a reliably long-term running operation, and then go after all the other byproducts that are now waste but can be useful as like the second phase.
I mean, if you have all the metals mixed together, right? I mean, it's
We
in
do
their
have
metals.
somewhat separated, so they condense out somewhat separate, and
You
they
don't,
just go
you
back together because they dump in the same pot.
yeah, you wouldn't even need to necessarily. I mean, you could go back to the electrochemical potential separation, right? So you could like say react these things like you know with chloride salts and you know, plate them out sequentially.
Mm. Yeah,
Because you already have their elemental metals. You don't even need a reducing agent at that point. The free energy's on your side, you know?
and another thing we are trying to achieve is to do a type of roll-to-roll process, not a batch type process. So we can process rather large quantities using a fairly small reactor, and plating things out. That sounds to me. I mean, I'm not an expert in that area. That sounds to me a very complicated process to turn complicated process to run on the lunar surface without humans and with very limited the consumables.
Maybe. I'm not saying that any of this is easy. So
Probably wouldn't be here if that was, right?
yeah, I mean, you know, that's why we have these discussions. So, but you know, like if you think about, well, if you think about any separation, I mean, what's the difference between these elements, right? I mean, it's their orbitals, right? It's their like they have different electrochemical potentials. If it's better to heat them up and like say gaseous irons, you know, condenses it this versus condenses it that, well then I mean you still have to bring up all the distillation equipment.
Oh, but that's not the only issue, because back reaction is going to be a problem. If you look at the Magsonic process from Cyro, they are the closest I've seen to solving back reaction for, they're making carbothermal magnesium. And so you get magnesium gas and carbon monoxide gas at like 2500 C, and they quench it in a shock wave to get them 10 or 100,000 degrees a second sort of cooling rates, and still the yield's not great, but they get some metal. So it's going to be a problem. Maybe there's a way around it, but this is going to be something that you're going to have to solve to make this work.
Even with back reaction, if you get as an outcome oxygen, silicon oxide is a glass. Glass is a useful material. Heavily oxidated iron, heavily oxidated aluminum, heavily oxidated titanium, and the leftover. That's already useful, because if you have just ore, iron oxide, then from that material it is possible to get iron.
Oh, I agree. And you know, maybe if you're getting 10% or 30% of the oxygen out, that's still useful, and the material that's left will be a better feedstock for a reduction process.
That's right. If you just regulate into elemental oxides, that's already great.
So have you run this reaction and produced some kind of basically like mixed metalloid slag at this point?
So we did. We ran this reaction at high temperature for some time, but we just started now to instrument it so we know how much we evaporated and what we evaporated. We haven't been able to evaporate the slag completely, probably not even close. We have on a condenser we have what's called droplets of stuff that condensed, but we haven't really looked at what has condensed in what form or how much back reaction did occur.
Right. So that's kind of in our upcoming, series of goals here. Is step number one was achieve the critical temperatures that we need to actually, kind of prove the core value here, which is reaching the point where, yeah, we do actually start getting all these other products out. And now we have to go about the process of characterizing that, instrumenting it, and moving forward from there. And also, we're still working on improving our efficiencies, improving our peak temperatures, but right now we're running around 2000 C just with our ground prototype here. And I don't know if you get a sense of scale from like the kind of instrumentation around it, but it's something you'd like hold that tube in your hands with two hands. It's that kind of size.
So is this work being funded through NASA or a space agency, or is this a private effort?
So our current funding is not actually something that we're allowed to publicly disclose at this time. But we are always on the lookout for additional opportunities and partnerships where, like, who knows, hey, you can get really high temperatures and you were originally looking at oxygen, but maybe other people have a different idea based on what this might unlock for them. So, I think we're open to all sorts of things, but I can't publicly disclose our funding at this time.
Okay, because I was just, I try to keep abreast of as much of the work going on as possible, and I hadn't seen this before, so I was just curious.
Well, yeah, this is our first public debut, you could say, is this conference. So,
okay, well, I'm glad I was here for the.
Yeah. So we've been working on this, for a few years, but we are now just kind of starting to share it with the world because we've reached a stage where we think it's ready to start sharing and then build on where we are right now to something better. So, yeah, I mean, if we ever have specific opportunities to discuss, kind of in private, I'm sure we'll be able to, talk in more detail about specifics.
Hey,
Yeah.
Gio, this is Kirby Runyon with the Lunar Surface Innovation Consortium, and I just sent you an email. This is really fantastic technology you're debuting, and I just have to wear my LSIC, my Lunar Surface Innovation Consortium hat right now, and plug that. If anyone here is not a member, I'd encourage you to go ahead and do that at lsic.jhuapl.edu. This is really exciting, Gio.
Yeah, thank you. And I did get your email, so I've been busy with the conference today, but we'll respond, after everything settles down and just go from there.
Jerry, it sounded like I interrupted you. Sorry about that.
No worries. And I also, Eric, feel free to stop me. I don't want to hijack this whole session with just our stuff, but I did want to, since the specific question was brought up, share our capabilities and where we're aiming to help, see where the discussion goes from there.
Yeah, on a similar note, the question about, hey, Regolith has lots of stuff. Why are people only looking at one individual process? Part of that is, funding wise, but part of it is also the fact that we do recognize that whatever comes out of one system could be the feedstock for something else. Mm-hmm. So, we recognize that many of the processes that deal with oxygen extraction will leave, either a powder or, some kind of a melted ingot of concentrated stuff mm-hmm. that somebody else can now come and take. So we, in all of our planning, we do recognize that tailing piles will be created and marked mm-hmm. from every process, such that it now becomes potentially the feedstock for, thermal storage or construction or further refinement.
Yeah, absolutely. And I think that it's going to be one of those things that evolves over time, right? We started trying to make an oxygen processor, but in the process of making oxygen, we're making an awful lot of silicon monoxide and hey, maybe that's a useful material to be used, in making these ceramic tiles. Like that's all gonna, come together. But, we're here trying to share people what we've been working on, because who knows what kind of little spin-off things people might want from achieving, these levels of, separating out the base minerals. And, as of right now, I think we're pretty open-minded to just see where the needs are. And, if we have the core technology, working at a high level, then we can always add complexity later.
Well, I would really, and my original question, kind of was going towards this. I'd really be interested in the resulting products, like the metalloid products that come out in terms of separation.
Are there any specific products that you would hope to have, or you just are really curious what they are?
No, because I have some other research things that basically where I'm looking at convenient ways of separating these apart. Right. And if they're in metal form, especially, even the oxygen is makes it a little bit harder, right? Because the oxide's fairly strong.
Right.
But if it's free metal, I mean, that's a lot easier from my perspective. And I'm right now I'm investigating just general way of basically separating these metal species out. And one thing I'm looking for is I'd love to have material that's representative of other processes too to evaluate, versus having these simulating materials that doesn't necessarily represent, let's say, an actual process.
Mm-hmm. Right. That makes a lot of sense.
Yeah.
It seems that you're going to need a pretty heavy duty thermal dump, right? You're going to have metals at thousands of degrees coming out that you need to bring back down to 200 Kelvin or something. You're going to have a huge set of radiating panels, would be my guess. Have you thought about that kind of the thermal constraints of working in a vacuum?
So yeah, pretty much all the energy we put into that thing comes out, and most of it comes out as heat. So most of our heat is fairly high temperature. So radiating this out is not so difficult. Maybe if you did energy recovery on that, then radiating out at a lower temperature would be more difficult. The low quality heat that comes mostly from electronics that have to stay well below 100 C. And we're hoping that is going to be only a small fraction in the 5% range of the total energy output. Mm-hmm. So we can radiate very hot. It doesn't require super large radiators.
And like we said before, we think that roughly around 20 kilowatts of power is sufficient with losses and with duty cycle considerations taken into account to do, 1,000 kilograms of oxygen per year. And, that'll be refined as we get more and more pieces of the puzzle integrated and then tested together. But that's like the rough power that we're talking about here. So, if we're trying to produce, tons and tons and tons of metal feedstock for things, that's going to be more power and more energy that needs to be radiated out. But at least at the small scale, like this reactor right here, if you go and you put your finger where the thermal reflector is, you don't burn yourself. It's actually quite comfortable. But it's not so comfortable if you go outside the thermal reflector. So there is a lot of heat there.
Yeah. I think we got about 30 seconds. When the cooling fails, we got a 30-second window before the thing implodes.
It's pretty hot. So.
Yeah. So anyways, I don't want to hijack this discussion with our slides because we already had the option to present it, but we're more than happy to keep talking about this, or, offline after this convention, or sorry, not convention, seminar, workshop, whatever you want to call it. that's my contact info there. We can have conversations offline and just carry things on. But thank you. I don't want to hijack things any longer.
No, I mean, I thought it was a good discussion, So
very interesting technology. Thank you for discussing it with us in more detail. We've had a couple questions in chat for two different areas that people think we should have some discussion on that we haven't yet. One of them is liquefaction technologies, and the other is beneficiation of minerals. So I don't know, let's start off with liquefaction there. So I guess the question is, we're producing oxygen, we're producing hydrogen, potentially other gas species. What are the gaps for liquefaction, and how can we move forward towards solving those problems or filling those holes?
Before the problem, you have to define the problem, because if you produce oxygen on the pole in the crater where at the bottom temperature is 25 kelvins, liquefaction is not a problem. You have a source of low temperature, you just put oxygen there, it becomes liquid, the pressure is pretty low, you pressurize the vessel and everything is fine. If you do the same thing at 300 kelvins, then you need cryogenic technology on the moon. And luckily, lunar regolith contains all chemical elements which are needed for power generation and for cryogenics. It is possible to make magnetocaloric materials from lunar regolith.
But what's the power generation? What are you referring to there specifically?
Different people have different preferences. Russians prefer to put a megawatt class nuclear reactor on the moon. People from the US rely on solar panels. On the moon, there are huge temperature differences. There are temperature gradients. There are temperature changes. There is a difference between temperature of deep space, which is 3 kelvins, and surface of the moon. And the moon has no atmosphere. So energy generation, opportunities for energy generation are tremendous.
Okay, I mistook what you said. I apologize. I thought you were talking about batteries for a second, which is that's another topic. So
I'm not sure if people can produce batteries from lunar regolith from dirty elements, but it is definitely possible to produce capacitors.
Well, I mean, there's sulfur, right? So there's sodium sulfur batteries are a thing. Not much sodium. I mean, there is sodium, but it's blowing off constantly. So
you should remember that batteries emit gases, even sulfur batteries. And the surface of the moon is vacuum. If gas is lost, the battery is degrading pretty quickly.
Yeah, no, I hope that.
And capacitors do not degrade.
Yeah, I was hoping that the sulfur battery might be in a container, not just sitting there. So, but anyways, I understand.
Liquid metal batteries.
The what? Sorry.
Liquid metal batteries.
Yeah, there you go. That works.
Mm-hmm. So the point was raised in chat, and it's a good point though, that while the permanently shadowed regions are in fact quite cold, there's not really much of a well to dump that heat into, as the regolith is such an amazing insulator. So I guess my question there is it really, will liquefaction really not be a problem in these regions for a very long period of time once you start condensing oxygen and hydrogen in that environment?
Along those lines, I guess I was curious to know if there's been any thoughts on doing an end-to-end kind of demonstration of extraction all the way to liquefaction and storage and transfer, because as you're I've seen the different parts of this ISRU process in isolation, but as you're moving from one part of the process to another, there are inevitable losses that you're going to be seeing, and it would be nice to see a full end-to-end demonstration of and I realize that there's a large number of competing technologies at this point, but
So yeah, if you look at some old papers going back to Constellation, we ran several analog field tests in Hawaii. The first one in 2008, we had basically excavation through the production of oxygen, gaseous oxygen, through two different hydrogen reduction methods. In 2010, we had a field test where we looked at all the steps associated with excavation all the way to liquefaction of oxygen through carbothermal reduction. And then as part of our new Artemis program, you know, as I mentioned earlier today, the goal is to have an end-to-end process on the moon by the end of the decade at a pilot scale. So we are working towards putting all the pieces together, including, you know, the excavation, the regolith transfer, any beneficiation or size sorting, the regolith reduction, the oxygen production, and the liquefaction and storage.
So Jerry, are there any pieces of that you think would need development in a lunar environment rather than terrestrial development?
Well, yeah. So basically what we've said is we're trying to do everything as much as possible on the ground, and we wholeheartedly support the idea to putting time on hardware as much as possible. But we also do recognize that there are specific aspects of the moon that are very difficult to simulate on Earth. So, you know, first of all, the simulants are only so good. So anything that interacts with actual lunar regolith, whether it's the excavation devices, the flow devices, the oxygen or metal extraction units, you know, do they operate the same way on the moon as they do on Earth? Is there a, you know, I won't call it a contaminant, but are there ingredients in the lunar regolith that might be at very low concentrations that we ignored in our ground testing that suddenly bite us in the butt? I don't, you know, and then, you know, cleaning techniques. Are the cleaning techniques for the water or the oxygen, you know, as good as we think they are? So yes, a final verification of all the steps in the lunar gravity, in the lunar environment with, you know, the regolith that's on hand, we think are, you know, incredibly important steps.
Sure.
I think what is missing is the fact that a lunar surface is vacuum, and a long-term storage of liquids in vacuum environment results in losses, and those losses can be pretty huge. An alternative is a solid-state storage. For example, on the Earth, there was a program for solid-state hydrogen storage, and using solid-state hydrogen storage devices in a given volume, you actually can store more hydrogen than in a compressed gas tank or even in liquid hydrogen.
Yeah, I mean, for oxygen, I think you know, that's a soft cryogen. I think, you know, there are issues with, you know, that actually help you in a vacuum. Your MLI operates obviously much better. If, you know, depending on your shielding, you can constantly view the 4K night sky. But I agree that when you start talking about a hard cryogen like hydrogen, you know, the leakage issues, the power issues opens up other possibilities potentially. And if you don't need the hydrogen as itself, you know, storing it as a different commodity even, I ran numbers. Methane actually stores hydrogen in a denser form than liquid hydrogen.
I think that there will be a need to design materials for solid state storage of volatiles on the moon in vacuum environment. Right now, I see funding for that.
Rockets can't burn hydrogen in solid state. It needs to be liquid hydrogen for a rocket engine to burn it. So
Well,
we're going to have to store.
For rockets, oxygen has to be liquid, but it should become liquid for a short time just before the launch. We reliquefy oxygen from solid state storage. The rocket is fueled, it is launched, everybody is happy. There are no losses. Hydrogen is not the best fuel because hydrogen is a critical element on the moon. Moon does not have a lot of hydrogen. Fuel should become different. As fuel on the moon, people can use liquid metals like liquid sodium, which is abundant.
Or you use aluminum.
Yeah, I mean, you could use warp drives too, but liquid hydrogen is what we build rocket engines to burn. Right? I mean,
yeah, it's hard to.
My other life before ISRU was chemical propulsion for human spacecraft, and I know the propulsion community, and they are very conservative. So it was hard enough to get them to move towards methane and as a possible fuel of interest versus kerosene on Earth or ox hydrogen. Coming up with a propulsion system that uses a solid fuel or aluminum or magnesium or silane, they're all possible, but I don't think at least NASA is not interested in developing those technologies. Maybe a company is.
Yeah, it would be hard to compete with the specific impulse that you're going to get from hydrogen in a chemical propulsion system. So that in itself makes it very difficult to have other things compete.
I mean,
it's years and decades, years and billions to design a new rocket engine on Earth. Right now, you're going to design it on the moon to use lunar fuel. Yeah.
So, I mean, I see it. It's different time phases. Like near term, hey, we've got LOX hydrogen Centaurs. It's a tried and true, high specific impulse liquid rocket engine. It's what a lot of people are using. That's great. But if we're talking about like mid to late term sustainable, infrastructure where you're not sending a bunch of refueling tankers, but Earth living off of the moon, at least in my mind, I see it more as a hybrid where you produce and condense oxygen, but then because you're processing other minerals on the moon, you can make solid fuel cores relatively, I won't say easily because no one's doing it right now, but the materials are there to do that. Whereas hydrogen, one, it's scarce, and two, there's no density and you need a lot of it. So that would be a lot trickier to refuel, say, a SpaceX Starship with lots of hydrogen if we're just trying to get it from naturally occurring sources on the moon, in my opinion.
Yeah, I mean, yeah. I'm more interested in once Artemis 9 has finished, NASA doesn't just leave the moon again, right? So I'm much more interested in what is the ISRU potential in the very near term.
And if you don't make it, you have to bring it from Earth, land it, and then take it off again.
Yep.
And the economics are just really bad for that.
And mass ratios.
Okay, really good discussion there. We're getting close to the end of this session, so I want to move on to the other topic that was suggested for conversation, just to make sure we have time to hit on it. That is a discussion of the beneficiation of resources on the moon. I guess the purpose of that would be how do we process needs to separate out the components that we need to simplify, either to recover usable components or to simplify our further refinement processes. So what is the state of the art for that technology? What areas are we lacking that we need development in? Sure, Jennifer has some suggestions on this, since I know you were one of the ones who made a comment there.
Well, there's all kinds of things that we could potentially do to help out with beneficiation. Just continue to develop things like sieving to be able to, you know, if we want to dissolve regolith up, we'd probably want something with a greater surface area for more reactivity. So we'd probably want smaller grain sizes to go into the processing. You know, if there's something that doesn't accept, you know, rocks in the processor, we'll need to remove those as well. There's also the mineral beneficiation aspect of things. If you're spending all this time and energy processing, you know, feldspar or something, you're going to want the concentration of feldspar to be greater in whatever your input is, so that your process is able to do that. You have less waste products. Same thing with the other different minerals that you would want to use, but there's a whole bunch of different mineral separation techniques that are used in the mining industry today, but we don't really have anything that is ready to go to flight. So this would be, like, to me at least, one of the first steps after excavation to our ISRU processes.
Hi, Jennifer, this is Paintball. I made a comment about beneficiation. So I'm in the mining industry, so my background is mineral processing. I strongly agree with you, like beneficiation should be the first step of everything, because, like, you know, like all the process that I can see depends on the certain minerals. But, you know, like there are not many studies being done in the literature. I mean, the only possible techniques they studied in the past were electrostatic separation and magnetic separation. And they only, like, those studies were only focused on one type of mineral, like most of them are emanite, I think. But yeah, so it's a very important topic, but at the same time, it's very challenging. Talking about the size classification, I think, like, it sounds easy, but actually it's not, because on Earth, the size classification is basically depending on the gravity. So we just don't know, like, how the reduced gravity on the moon will affect the effectiveness of the screening process.
Well, and even on Earth, when you get the really fine stuff, even on Earth, gravity doesn't work very well. At least it has to have fluid assistance.
Yes, exactly. I mean, most of the time, I mean, if you look at almost all the process in mineral processing, we need to have processed water. So, I mean, that's a big limitation on the moon. I mean, there's water in it, but we definitely don't want to use water to assist the beneficiation process.
Like, one of the things we need to be very careful about, and I wholeheartedly support Jennifer in her discussion about size sorting and mineral beneficiation, is the fact that you know, the simulants we create on Earth may give us false confidence in the processes that occur on the moon, which will have a much wider range of minerals and shapes and such. It's because I think whether it's, you know, an oxygen or metal extraction technique or some kind of construction technique that you know, requires interlocking through binders or heating or whatever, you know, we may find that we desire certain size fractions or certain minerals. And we started to see this to some extent during the Constellation program when we were using fluidized beds in hydrogen reduction to, you know, reduce the iron oxides, where, you know, we found that the reaction rates and the fluidization versus you know, velocity versus reactor height was strongly a function of the particle sizes. And so we, besides just, trying to concentrate the iron oxides, we recognize that we wanted to have certain size classes, nothing too small, nothing too large, to also increase the performance of our extraction process.
And all the details will be process specific. For your example, with the fluidized bed, yes, it has to be a very narrow range of particles, but you can design for almost any particle size. You just have to pick one. And if you're trying to dissolve it, you want all the fines that would have been elutriated from your fluidized bed. And if you're melting it, then anything that fits in the hole, and so on. It depends on what you're doing. For some of the other construction things, you'll want 2 or 3 or 4 different narrow size ranges.
Well, and it gets to consistency of product, in construction, whether it's manufacturing or, if your process, how does your product vary, the hardness or stiffness or whatever the case may be, if you don't control the feedstock material.
Yeah, and that's a good point. The other point is, like, if you look at the size fraction, maybe there are certain minerals, they are enriched in certain size fraction. So that's something we typically see on Earth, like for like the mineral processing business we do here. So size classification is very important, but I just wondering whether NASA is currently doing any sort of beneficiation related work. I mean, like, what kind of technology or development you guys are currently studying? Are those, if you do have some, are those familiar, similar to the ones used in the mining industry, or is
I mean, at the moment, we've we did, as you pointed out, ilmenite beneficiation through tribocharging and electrostatic separation. Pioneer Astronautics has a SBIR sequential that's looking at size sorting and once again, iron oxide mineral concentration beneficiation. And then I believe there is a luster call out on the street for now new research in mineral beneficiation and size sorting.
Yeah.
The notice of intent for that is due tomorrow.
Woohoo! What are you doing here, Leslie? You should be writing something.
I have minions to do that.
Oh, yes. It's always good to have minions.
Yes.
So can I put together a couple of pieces that people have been talking about? What mineral form is the iron in the highlands? Is it dissolved or wustite or ilmenite or what?
In the highlands, there's a little bit of ilmenite, and there's the nanophase iron, and there's a small amount of iron in the feldspars in the ferronanorthozites.
Okay, so the nanophase, is that iron metal then?
Yes, it is. It's native iron.
Wow, fascinating. I never
But
would have imagined.
extremely small particles.
Extremely nanophase.
Yeah, like nano
Emphasis
size.
on nano.
Do you know, like, the weight percentage, like how much nanophase iron is in there?
Not off the top of my head. I know it's very small, and it really depends on how long the material has been exposed to the lunar environment, the surface lunar environment.
Yeah, okay.
Yes, it seems that maturity of the regolith, all else being equal, is a good indicator of the nanophase iron content, which is within glass rims around particles. It's not just lying out free.
Where I was going with this was that if you're moving, say, 1,000 tons for a blast pad, and you care about the size distribution there, then maybe something that's only 2 or 3 or 4%, if you can get half of it through beneficiation, that starts to be a real noticeable feedstock.
Yeah, a nice byproduct of construction.
And the beneficiation would have to be integrated into all these processes. But if you've got to move it anyway, and you've got to classify it anyway, then maybe you can change the way you do that subtly to get a feedstock stream.
Very likely. In fact, a significant portion of gold produced, at least in this country and probably most places, comes from a little step in river gravel processing. Just a little basically astroturf to trap little gold particles, even if it's not an actual big enough or rich enough to be a placer deposit. There's still some, and so it's a nice little product stream and a byproduct of gravel mining.
Oh wow.
All right. Well, hard to believe our time is up here. It's been some very interesting discussion. Thank you, everyone, for taking the time to come here and provide inputs into this topic. So we will, we've got a note taker who's been recording all this. I've been taking notes. We will be compiling everyone's input, and it will be submitted to the conference organizers so that there's a record of what's discussed here. So it really does have an impact on formulating where things are going to go from here, where research will be done. Other than that, I think that's where we are. We're done. So thanks again to everyone. I guess have a good evening.